Jupiter used to be just a colorful blur in science books, a giant ball of gas, too far to touch and too mysterious to fully understand. But that's changing fast. Right now, we're witnessing the most detailed, most stunning, and most unbelievable real images of Jupiter ever captured. Pictures so sharp they almost don't look real. And no, this isn't CGI. These are actual photographs, some taken just weeks ago by NASA's Juno spacecraft, as it dives past the gas giant in its wild elliptical orbit. Others were captured by telescopes, like the James Webb and Hubble, teaming up to scan Jupiter in infrared, ultraviolet, and visible light all at once. And some of the most beautiful shots, they were stitched together by regular people, citizen scientists, processing raw NASA data and turning it into planetary art. But here's the weird part. As we zoom in closer, things only get more confusing. Jupiter's clouds are doing things we didn't expect. Its famous Great Red Spot is shrinking, and not just slowly. Massive storming and disappearing in days. And deep inside its atmosphere, there are hints that Jupiter may have a hidden core stranger than any planet we've ever studied. This isn't just a bunch of pretty pictures. These images are changing how we understand planets, storms, moons, even the early days of our own solar system. Let's take a deep dive, not just into the most jaw-dropping images, but into what they're really telling us about this colossal world. What are we really seeing? And what secrets is Jupiter still keeping behind those swirling clouds? The transformation in how we see Jupiter represents nothing short of a revolution in planetary science. For centuries, Jupiter remained one of the most enigmatic objects in our night sky. Ancient astronomers noted its brightness and movement, but could only speculate about its nature. With the invention of the telescope, Jupiter became slightly less mysterious, revealing its distinctive bands and its famous red spot. But the details remained frustratingly obscured by the limitations of Earth-based observation and the vast distance separating us from this enormous world. The Voyager missions in the late 1970s provided our first close-up looks, revealing a staggeringly complex system of storms and colors. Yet even those groundbreaking images seem quaint compared to what we're seeing now. The modern era of Jupiter observation has ushered in a level of detail and clarity that would have seemed impossible just 2 decades ago. We can now resolve features smaller than Earth itself, track individual storm systems over months and years, and even watch the planet's atmosphere evolving in real time. This newfound clarity has fundamentally challenged many assumptions scientists held about how gas giants work, how their atmospheres circulate, and what drives the enormous weather systems that rage across their surfaces. What used to be a blurry mix of brown and red bands is now a canvas of deep blues, pale pinks, icy whites, and stormy grays. Some look like marble, others like ocean waves frozen mid-motion, but all of them are real, and they're coming straight from the edge of space. Most of these images come from Juno, the camera aboard NASA's Juno spacecraft. It wasn't even designed for hardcore science. It was just supposed to give us some nice pictures for the public. But what happened next surprised everyone. People around the world started downloading the raw image files and processing them on their own. Artists, scientists, they all jumped in. And what they've been creating with that raw data looks like fine art that just happens to come from 500 million miles away. One photo shows a massive cyclone that looks like a hurricane on steroids, except it's the size of Earth. Another captures a cluster of storms swirling like petals in a flower. And some of the cloud patterns are so detailed they show shadows from different layers of Jupiter's atmosphere. You can literally see depth in a planet made almost entirely of gas. And these aren't isolated moments. Juno has been flying Jupiter since 2016. But the recent images are getting better with every pass. Why? Because Juno's orbit is gradually bringing it closer and closer during each flyby. That means higher resolution, more detail, and better lighting angles. Sometimes you can even catch sunlight just graze the edge of a storm, like a sunset on Earth. But over a place where it rains ammonia, the craziest part, we're seeing things that nobody expected. Strange bright spots, new storm systems, tornado-like features twisting around the poles, and a layer of haze high above the clouds that changes color under different light. The decision to make Juno Cam a public-facing instrument may have been one of the most inspired choices NASA has ever made. By releasing raw image data freely to the world, the space agency unlocked the creativity and passion of thousands of amateur astronomers, digital artists, and enthusiasts who saw an opportunity to contribute to science in a meaningful way. These citizen scientists, working in their homes with personal computers, have developed increasingly sophisticated techniques for processing Juno's raw images. They've learned to combine multiple frames to enhance resolution, adjust color channels to reveal otherwise invisible features, and apply advanced filtering algorithms to bring out subtle details in Jupiter's atmosphere. The results have been stunning. Some of the most breathtaking images we have of Jupiter haven't come from professional imaging teams, but from passionate individuals who donated their time and expertise because they wanted to help us see Jupiter more clearly. This democratization of space exploration has proven invaluable, not just for public engagement, but for actual scientific discovery. Citizen scientists have spotted new storm systems before professional teams, tracked the evolution of atmospheric features over time, and created visualizations that have helped scientists themselves better understand what they were looking at. The collaboration between professional astronomers and citizen scientists has become a model how modern space exploration can work, combining the rigor and resources of established institutions with the fresh perspectives and creative approaches of an engaged public. This isn't just photography. It's like we're finally seeing the personality of Jupiter, a living, moving, shape-shifting world that's more complex. It doesn't just spin, it breathes. And for the first time, it's not hiding that from us anymore. The key to understanding why Jupiter's personality has become so apparent lies in the combination of technological advances and orbital mechanics that have aligned perfectly over the past few years. Juno's gradual orbital decay brings it ever closer to Jupiter's cloud tops with each pass. Each approach provides opportunities to capture imagery with progressively higher resolution. The spacecraft's camera, despite being designed as a scientific instrument, captures visible light images in an exquisite detail when aimed at the right targets during the right moments. The timing of these observations, coordinated with observations from other telescopes and spacecraft, creates a symphony of data that reveals Jupiter in unprecedented ways. What we're seeing is not a static planet at all, but a dynamic, evolving world where weather systems are constantly forming, intensifying, weakening, and disappearing. Storm systems that stable in one image can evolve dramatically over the course of a few days or weeks. New cyclones can suddenly appear where there was calm weather just weeks before. Anticyclonic systems can merge or fragment. The interplay between different atmospheric layers creates complex three-dimensional structures that science fiction writers could never have imagined so vividly. When scientists see these images, they're not just admiring the beauty of an alien world. They're reading a record of atmospheric processes, energy transfers, and fluid dynamics that everything they thought they understood about how planetary atmospheres work. The atmosphere isn't behaving in the neat, simple ways that older models predicted. Instead, it's revealing itself as a far more complex system with unexpected feedback mechanisms, surprising interactions between different atmospheric layers, and behaviors that our current understanding of fluid dynamics doesn't fully explain. But as beautiful as the planet looks from above, things get even weirder when Juno starts flying low, close enough to make out every wrinkle in Jupiter's stormy face. The most recent flybys from Juno weren't just lucky shots. They were planned dives timed precisely pass within a few thousand kilometers of Jupiter's cloud tops. That's basically scraping the edge of a planet made of storm. And what Juno saw on those passes, it's the kind of stuff you expect from science fiction, not real-life space exploration. Take the Great Red Spot. It's been raging for at least 300 years, maybe longer. But now, for the first time, we're getting real high-resolution image show just how complex it actually is. The red spot isn't just a storm. It's a layered monster. Think of it like a storm inside a storm, spinning within deeper currents, almost like it's anchored below the clouds. Juno's latest images show fine structures, ridges, swirls, even smaller vortices being eaten alive by the larger storm. It's like watching a giant eye blink, slowly as smaller clouds get pulled into it and disappear. Even more strange, the red spot is getting smaller. That's not new, but now we can track how fast it's happening. It's shrinking in width, but getting taller vertically, like a storm turning into a skyscraper. That's something we didn't predict. The mechanics of that behavior are still a mystery. Juno also flew over Jupiter's north pole, and if you've never seen it, it doesn't look anything like the Jupiter you know. Up there, storms don't swirl in neat bands. They clump together in massive polygonal arrangements. There are literally 7, sometimes 8 storms, all spinning around a central vortex, each one perfectly spaced like petals around a center. Scientists call them circumpolar cyclones, and they stay locked in place like they're frozen in a dance. But they're not frozen. They're raging hurricanes bigger than Texas, spinning for years and still holding formation like some kind of atmospheric ritual. And between these massive formations, deep blue voids, regions that seem calmer, but may hide faster, denser flows underneath. No other planet has anything like this. Not even close. The Great Red Spot has captured human imagination for centuries, but our understanding of it has been almost comically limited until very recently. Observers centuries ago would note its presence and describe its reddish color, but could say almost nothing about its actual nature or structure. Even with modern telescopes, from Earth's surface, the great spot appeared as an elliptical blob of reddish coloration, roughly 16,000 kilometers wide, with some internal structure visible, but largely inscrutable. The advent of spacecraft observation allowed us to see more detail, but the Great Red Spot remained limited. Now, Juno's close flybys have revealed that the Great Red Spot is vastly more complex than anyone had imagined. It's not simply a rotating mass of gas circling a common center. Instead, it appears to be a layered structure with multiple rotating components at different depths and velocities. The outermost edge of the storm shows one rotational pattern, while deeper layers rotate at different rates, creating a shearing effect that should, by conventional fluid dynamics, tear the storm apart. Yet it doesn't. Something is holding it together, and we're not entirely sure what. Perhaps there are deeper, stable structures that anchor the visible storm, or perhaps the chemistry of Jupiter's atmosphere creates interactions between different chemical species that stabilize the structure in ways we don't yet fully understand. The fact that the Great Red Spot is shrinking has been known for decades, but geometry has revealed the nature of that shrinking in unprecedented detail. It's not simply contracting uniformly. Instead, it appears to be transforming, becoming more compact and more vertically extended. This transformation suggests that the energy sources driving the storm may be changing, or the storm's interaction with the surrounding atmosphere is shifting in fundamental ways. Perhaps the storm is converting lateral motion into vertical motion, becoming a more tightly wound, higher-reaching structure. Or perhaps the surrounding atmosphere is gradually eroding edges while the core intensifies. Whatever is happening, the Great Red's evolution is teaching us about the long-term stability of atmospheric structures and how they respond to changing conditions. The circumpolar cyclones at Jupiter's poles represent perhaps the most alien weather system that exists anywhere in the solar system. Imagine a hurricane so massive that you could fit multiple Earths inside it. Then imagine not one, but a ring of 6 or 8 or more of these hurricanes, all rotating in the same direction around a pole, evenly spaced as if arranged by some cosmic architect. Each one maintains its position relative to the others, creating a geometric pattern that seems too perfect to be natural. Yet it is. These storms have been locked in this configuration for at least as long as we've been able to observe Jupiter in detail. They don't merge, they don't scatter. They maintain their formation like performers in a cosmic ballet that has been running for decades or much longer. The existence of these polar cyclones has profound implications for how we understand atmospheric dynamics on gas giants. On Earth, weather systems are generally driven by the temperature differential between the poles and the equator, coupled with the planet's rotation. Atmospheric circulation tends to move heat from the equator toward the poles, but Jupiter's poles are actually warmer than they should be based on the amount of solar radiation they receive. This suggests that there are mechanisms heat toward the poles from the lower atmosphere, keeping them warmer than simple energy balance would predict. The circumpolar cyclones may be playing a role in this heat transport, or they may be a consequence of it. Either way, their existence forces us to reconsider how energy circulates in gas giant atmospheres. Some scientists hypothesize that the hexagonal arrangement isn't a coincidence, but rather a consequence of specific mathematical properties of rotating fluid systems. When you have a fluid rotating at different rates at different latitudes, certain geometric patterns become energetically favorable. The fact that Jupiter settles into this hexagonal arrangement suggests that it's the natural state toward which the system tends to evolve under the constraints of Jupiter's rotation and atmospheric properties. During one of the more recent passes, Juno even caught brief glimpses of fast-moving, high-altitude jet streams. Jets were invisible to previous spacecraft, but now they're showing up as streaking across cloud bands like scars. Evidence that Jupiter's atmosphere is layered in we barely understand. And here's the twist. Many of the best images weren't even expected. Juno wasn't designed for long-term imaging, and it wasn't expected to survive this many orbits. But it did, and it's still going. With each orbit, Juno keeps getting better shots, closer data, and more surprising results. These high-altitude jet streams are particularly puzzling because they move incredibly fast, far faster than the wind speeds predicted by atmospheric circulation models. They seem to exist at a different altitude from the well-known zonal wind bands that dominate Jupiter's visible atmosphere. This suggests that Jupiter's atmosphere has more vertical structure than previously appreciated, rather than being a relatively homogeneous mix that circulates in simple patterns. It appears to have distinct layers with different properties, different wind patterns, and different chemical compositions. Understanding how these layers interact with each other will require a fundamental rethinking how we model planetary atmospheres. One possibility is that the high-altitude jets are a result of complex three-dimensional dynamics that can only occur in the specific conditions found in Jupiter's atmosphere. Another possibility is that there are energy sources driving these jets that we haven't identified yet, perhaps related to atmospheric heating from above or complex interactions between different atmospheric layers. The persistence of Juno, well beyond its original planned mission, has been extraordinarily fortunate for planetary science. The spacecraft was expected to operate for perhaps 5 to 7 years before being deliberately into Jupiter to avoid any possibility of it crashing into one of Jupiter's icy moons and contaminating them with Earth microbes. However, the spacecraft has proven far more robust than anticipated, continuing to operate and return data even as its solar panels degrade and its instruments show their age. Each additional orbit brings new opportunities for observations, new angles on familiar features, and new chances to catch rare events that only happen occasionally. Just when you thought Jupiter couldn't get any stranger, its moon, Io, steps in and completely steals the show. It's alive, with plants or cities, but with volcanoes. Hundreds of them. Some of them are constantly erupting, and now, for the first time in over 20 years, we're finally seeing them up close again, thanks to Juno. During its recent flybase, Juno adjusted its path to swing past Io multiple times, and what it commonly looks unreal. Giants of material erupting straight into space. Lava lakes glowing faintly along the surface. Entire regions scarred and blackened by past eruptions. It's like watching a planet's fireworks show, but more violent and without a single moment of rest. In one of the clearest shots, you can actually see a volcanic plume rising above the edge of Io's horizon, backlit by the sun. It looks like a fountain of ash reaching hundreds of kilometers into the sky. And all of this is happening on a moon only about the size of Earth's moon, but constantly stretched and squeezed by Jupiter's gravity until its insides boil. That's the reason for the chaos. Io orbits so close to Jupiter and experiences such intense gravitational tugging that its crust is literally kneaded like dough. This constant flexing heats the interior, melts rock, and keeps the volcanic systems alive. In fact, Io is the most volcanically active object in the entire solar system, and here's what makes these new images so valuable. They don't just show eruptions, they show how Io's surface changes over time. Between flybys, scientists have started to track new lava flows, shape changes in volcano craters, and shifts in the thermal glow of the moon's hottest spots. One region that looked flat and calm a few months ago is now coated in dark, fresh volcanic deposits. We're literally watching geology in motion on a world where the ground never rests. Io represents one of the most extreme environments in our solar system, yet it's often overlooked in favor of the more mysterious Europa or Titan. To understand Io is to understand the consequences of tidal heating taken to its extreme. In the distant past, Io may have been a cold, geologically dead world. But its proximity to Jupiter, combined with orbital resonances with its neighboring moons Europa and Ganymede, trapped in a gravitational configuration that subjects it to constant tidal flexing. Jupiter's gravity pulls on Io, deforming it slightly. Meanwhile, Io's neighbors also exert gravitational tugs, pulling in slightly different directions at different times. This creates a kneading motion, an incessant squeezing and stretching of the entire moon. The gravitational work done on Io's interior generates tremendous heat, enough heat to keep vast regions of Io's interior molten or semi-molten. This heat must be radiated away, and the primary mechanism for that radiation is volcanic eruption. Io literally bleeds off its internal heat through its volcanoes. If Io were to stop having tidal flexing, it would gradually cool, and its volcanic activities. But as long as Jupiter holds it in this orbital configuration, Io will continue to erupt. The result is a world that is being continuously remade by volcanism. New lava flows cover old deposits. Sulfur compounds condense and freeze in continuous atmosphere, only to be stirred up again by the next eruption. Impact craters, if they form at all, are quickly covered by new volcanic material. Io's surface is one of the youngest, most active surfaces in the solar system, constantly being resurged by volcanism. The detailed images of Io's volcanic features that Juno has captured have revealed details that earlier spacecraft simply couldn't resolve. We can now see the fine structure of individual lava lakes, tracking how their brightness and distribution changes over time. Some lakes seem to be gradually cooling and solidifying, only to have nearby eruptions re-inject hot lava into them. Others flare with sudden brightness, indicating massive new eruptions from underlying magma chambers. The plumes captured in these images extend hundreds of kilometers into space, far higher than Earth's highest mountains. These plumes consist of sulfur dioxide and other volatile compounds that are ejected from Io's surface by the explosive power of volcanic eruptions. As the material rises, it cools, and the volatile compounds condense and freeze into particles that then rain back down onto Io's surface, creating deposits of frost and frozen volatiles around the volcanic vents. Over time, this creates distinctive patterns on Io's surface, with reddish and yellowish deposits surrounding the most active volcanic centers. The chemical composition of these deposits varies, reflecting the different sulfur compounds ejected from different volcanic regions. Some areas are dominated by yellow sulfur, others by darker reddish compounds, still others by icy deposits of frozen sulfur dioxide. By analyzing the colors and patterns in these deposits, scientists can infer which volcanic regions are most active, how long it's been since a particular region last erupted, and what the subsurface conditions might be like beneath the most active volcanic centers. But the story goes deeper than surface fireworks. These eruptions are injecting material into Jupiter's magnetic environment. Sulfur and plasma from Io's volcanoes actually become part of Jupiter's radiation belts. That's right. This tiny moon is helping fuel the largest planetary magnetosphere in the solar system. And the interaction isn't one way. Juno's instruments detected magnetic field disturbances and particle flows around Io that seem to shift depending on volcanic activity. That means Jupiter and Io are locked in a strange, violent relationship. Every eruption feeds energy into space, and every orbit twists the moon a little more. These aren't just cool pictures. They're a glimpse into an alien world that's tearing itself apart from the inside. And the closer we look, the more we realize Io isn't the exception. It might be the key to understanding Jupiter's entire system. The relationship between Io and Jupiter's magnetosphere is one of the most dramatic examples of how bodies in the solar system can influence each other across vast distances and through multiple physical mechanisms simultaneously. Io's volcanoes erupt, sending sulfur and other materials into space. Much of this material is ionized, turning into electrically charged particles. Jupiter's powerful magnetic field captures these charged particles, trapping them in radiation belts that encircle the planet. The presence of these new ions in Jupiter's magnetosphere changes its structure and behavior. The added material increases the density of the radiation belts, amplifies certain electromagnetic waves, and even affects the aurora displays visible at Jupiter's poles. In essence, Io is continuously supplying material that feeds Jupiter's magnetosphere, and Jupiter's magnetosphere continuously subjects Io to electrical currents and electromagnetic forces that may influence Io's own internal processes. Some scientists have speculated that the intense electromagnetic currents flowing through Io from Jupiter's magnetosphere might actually contribute to Io's internal heating, adding to the tidal heating already occurring. If true, this would mean that Io's volcanism is not solely a consequence of tidal heating, but is also partially powered by electromagnetic energy from Jupiter's magnetosphere. While Juno gives us those dramatic up-close shots of Jupiter's storms and surface chaos, it's not working alone. Thousands of kilometers away, two of the most powerful telescopes ever built, Hubble and the James Webb Space Telescope, have been quietly watching Jupiter from a different angle. And what they're seeing is just as strange. The James Webb Space Telescope, for example, turned its infrared sensors toward Jupiter. What it captured was something no human had ever seen before: a high-speed jet stream blasting through the planet at more than 500 kilometers per hour. The jet sits above the main cloud layers and moves so fast that it looks like a blur even in long exposure images. It's like a secret river of wind flowing across the top of the planet's atmosphere, totally invisible in normal visible light. At the same time, Webb picked up surprising heat signatures from deep within Jupiter's atmosphere. In some zones, the heat appears to rise from beneath mass storm systems, suggesting there's more vertical movement in the planet's interior than we previously understood. And in the polar regions, Webb's infrared eyes revealed glowing auroras, just like the northern lights on Earth, but stretched into massive, violent rings of energy powered by its intense magnetic field. Then there's Hubble. It's been watching Jupiter for years, but it's still contributing. Invisible and ultraviolet light, Hubble has been tracking long-term changes, storm evolution, cloud movements, shifts in color patterns. It sees the big picture while Juno gets close, and when their data is compared side by side, you start to see things that neither telescope could have revealed on its own. The contribution of the James Webb Space Telescope to our understanding of Jupiter has been particularly profound because it has opened up an entirely new window onto the planet's physics and chemistry. By observing in infrared wavelengths, Webb can see through layers of ammonia clouds that are opaque to visible light, revealing the deeper atmosphere beneath. It can also detect the thermal radiation emitted by warm regions in Jupiter's atmosphere, creating a heat map that shows where energy is being transported and where it's being radiated away into space. The high-speed equatorial jet stream discovered by Webb is perhaps the most remarkable recent finding. This jet moves at speeds exceeding 500 kilometers per hour, far faster than the typical wind speeds in Jupiter's visible cloud layers. The jet exists at a higher altitude than the main visible clouds, sitting above the ammonia layer, where visible light observations are blocked. The discovery of this has forced scientists to revise their models of Jupiter's atmospheric circulation. If Jupiter has one hidden jet stream in the upper atmosphere, it likely has others. The atmosphere may be far more complex and layered than previously appreciated, with multiple distinct circulation patterns at different altitudes, each potentially driven by different mechanisms, and each contributing to Jupiter's overall weather patterns. The heat signatures detected by Webb in association with storm systems are equally intriguing. These signatures suggest that storm systems extend deep into Jupiter's atmosphere, pulling material from warmer regions below and transporting it upward. This vertical circulation means that Jupiter's atmosphere isn't simply horizontally stratified, but has vigorous vertical mixing, with material cycling between the upper and lower atmosphere on relatively short timescales. The role of infrared observations in understanding Jupiter cannot be overstated. Infrared radiation at certain wavelengths can penetrate layers that are opaque to visible light, revealing the hidden depths of Jupiter's atmosphere. By observing at multiple infrared wavelengths, scientists can create a three-dimensional picture of Jupiter's atmosphere, seeing how temperature, pressure, and composition vary with altitude. Webb has been particularly effective at detecting the thermal radiation from deep atmospheric layers, allowing us to infer conditions in regions where we cannot directly observe visible light reflected from clouds. This has led to the discovery of atmospheric features that were completely unknown before, including unexpected hotspots, anomalous temperature distributions, and strange chemical signatures that suggest unexpected chemical processes occurring in Jupiter's deep atmosphere. The auroras at Jupiter's poles, observed by Webb and other instruments, are particularly fascinating because they reveal the interaction between Jupiter's magnetic field and its upper atmosphere. Like Earth's auroras, Jupiter's auroras are created when charged particles from the magnetosphere collide with atmospheric molecules, exciting them and causing them to emit light. However, Jupiter's auroras are far more energetic and extensive than Earth's, covering thousands of square kilometers and emitting enormous amounts of energy. The pattern of auroral emission, when analyzed carefully, reveals information about how magnetic field lines are configured near Jupiter's poles, where the most intense magnetic fields exist. By tracking how auroral features move and evolve, scientists can infer the structure of Jupiter's magnetic field and how particles are flowing through the magnetosphere. Some storms, for example, look tame in Hubble's wide shots, but up close, Juno shows them twisting and folding like giant whirlpools. Other times, Webb will detect a heat anomaly, and then Juno flies over the same region and finds something physically forming in the clouds: a rising tower, a new vortex, a fresh cluster of turbulence. This collaboration between missions wasn't even part of the original plan, but the discoveries coming from it changing how we think about Jupiter's weather, interior structure, and even its influence on nearby space. We're getting a full picture from the surface textures to the boiling depths to the cold, fast-moving jets in the upper atmosphere. Jupiter isn't just a giant ball of gas. It's layered, active, and constantly shifting. And with these combined from Juno, Webb, and Hubble, we're finally seeing it as a real dynamic world. Not just a distant dot in the sky, but a system with depth, motion, and mystery. The synergy between different observational platforms has proven extraordinarily valuable in ways that couldn't have been fully anticipated. When Juno provides high-resolution close-up images of a particular region of Jupiter's cloud tops, scientists can cross-reference those images with simultaneous observations from on Webb to gain context. Is the storm that Juno is imaging part of a larger system that extends across the planet? How does local weather at the location where Juno is observing relate to the planetary scale patterns that Hubble and Webb are tracking? By combining data from multiple sources, scientists can construct comprehensive models of Jupiter's weather systems that account for physics operating at multiple scales, from the few kilometer scale details visible in Juno's images to the planetary scale circulation patterns that only Hubble and Webb can fully capture. The ability to track storm systems over time by correlating observations from different instruments has led to several surprising discoveries about Jupiter's weather dynamics. Some storms that appear isolated and discrete in visible light images actually turn out to be connected to larger weather systems when infrared data is examined. Other storms seem to be triggered by the interaction between different atmospheric layers, with something that happens deep below the visible clouds eventually manifesting as a surface weather feature days or weeks later. These discoveries have led to a more complex and dynamic picture of Jupiter's atmosphere than was previously imagined. The atmosphere is not simply a collection of independent weather systems, each doing its own thing. Instead, it's a tightly coupled system where different scales of weather interact, where the large-scale circulation patterns constrain what smaller storms can do, and where local features sometimes trigger unexpected changes in the broader atmospheric circulation. This has profound implications for how we think about atmospheric dynamics on all planets, not just Jupiter. It suggests that models of planetary atmospheres need to account for interactions across a wide range of scales, and that understanding the big picture sometimes focusing on small details. It demonstrates that even after centuries of observing planets, we can still discover fundamental things we didn't understand before. The modern era of multi-wavelength, multi-spacecraft observation has created unprecedented opportunities to understand complex planetary systems in their full dimensionality. And this view is only the beginning, because there are 2 new missions already on their way to Jupiter right now. Missions that won't just take pictures, but will explore its moons, its ocean worlds, and its secrets buried beneath the ice. Right now, 2 spacecraft are hurtling toward Jupiter, and they're not going there just to look at the planet. They're going to dive into its moons, search for oceans, scan for signs of life, and do the kind of science that could redefine how we see our own solar system. The first is JUICE, Jupiter Icy Moons Explorer. It's a European Space Agency mission that launched into 2023. It's not expected to arrive at Jupiter until 2031, but when it does, it's going to focus on 3 of Jupiter's most fascinating moons: Ganymede, Callisto. These aren't just icy rocks orbiting a gas giant. All 3 of them are believed to have subsurface oceans, liquid water beneath kilometers of frozen crust. And JUICE is bringing radar, spectrometers, altimeters, and a magnetometer to figure out just how deep, how salty, and how alive those oceans might be. It'll be the first spacecraft in history to orbit another moon besides our own. That moon is Ganymede, the largest moon in the solar system. It's bigger than Mercury, and it's the only moon we know of with its own magnetic field. What's inside it? Why is it magnetic? What's lurking under all that ice? JUICE is going to find out. Then there's Europa Clipper, NASA's flagship mission, to one of the most exciting places in the solar system, Europa. It launched in October 2024 and is expected to reach Jupiter by 2030. Once it's there, it will perform dozens of flybys of Europa, scanning its icy surface with radar, sniffing for chemical signatures in the thin atmosphere, and maybe even detecting geysers shooting out from cracks in the ice. Europa is considered one of the best places to look for alien life in our solar system, not just because it has water, but because it has active water. The gravitational pull from Jupiter stretches and heats Europa's interior, creating the conditions that could support life beneath the surface. And Europa Clipper is being sent there to get as close as possible without actually landing. What makes these missions special is that they're building on everything we're seeing now. Juno gave us close-up shots. Webb and Hubble gave us the big picture. But JUICE and Clipper are going deeper, literally. They're going to study the stuff that's hiding beneath the beauty, the hidden oceans, the chemistry, the energy sources. The JUICE mission represents a major commitment by the European Space Agency to understanding the Jupiter system comprehensively. By the time JUICE arrives at Jupiter in 31, it will have been traveling for 8 years since its launch in 2023. The spacecraft carries an impressive suite of instruments designed to probe the nature of Jupiter's moons from orbit. The radar instruments will be able to see through the icy crusts of these moons, revealing the subsurface structure and potentially detecting liquid water beneath the ice. The spectrometers will analyze light reflected from the surfaces and emitted from the atmospheres of these moons, revealing their chemical composition and revealing clues about what processes are occurring in their interiors. The magnetometer will measure magnetic fields around the moons, providing information about their internal composition and the presence of conducting fluids like subsurface oceans. By focusing on Ganymede as the primary target for orbital operations, JUICE will be able to study this remarkable moon in unprecedented detail. Ganymede is the only moon known to have its own magnetic field, which is deeply puzzling to planetary scientists. The only way a moon so far from its parent star could generate such a strong magnetic field is if there's a liquid iron core inside, deep underground, capable of sustaining the electric currents necessary to generate a magnetic field through dynamo effects similar to those that generate Earth's magnetic field. But how could a moon the size of Mercury have retained a liquid iron core for billions of years? The answer likely lies in tidal heating, similar to what drives Io's volcanism. Ganymede experiences tidal heating from its gravitational interactions with Jupiter and its neighboring moons, particularly Europa and Callisto. This heating, combined with perhaps radioactive decay in Ganymede's interior, may be sufficient to keep a portion of the core molten. By studying Ganymede's magnetic field in detail, JUICE will help us understand how these processes operate inside this giant moon. Europa has long captured the imagination of planetary scientists and the general public alike, because it represents, arguably, the best place in our solar system to search for extraterrestrial life, at least with current technology. Europa is covered with an icy crust, but beneath that crust lies a global ocean of liquid water, possibly deeper and more voluminous than all of Earth's oceans combined. The existence of this subsurface ocean has been inferred from Europa's low density, its gravitational interactions with Jupiter, and its internal heat from tidal flexing. The evidence is compelling, though direct proof has yet to be obtained. The key insight is that Europa, like Io, experiences tidal heating from Jupiter. However, instead of melting rock, the heats ice from below, creating a liquid water ocean beneath the frozen surface. This ocean, separated from the vacuum of space by a kilometer's thick ice layer, is nonetheless in contact with Europa's rocky interior. Chemical gradients between the warm, rocky interior and the cold water above should drive chemical reactions and the transport of energy-rich molecules into the water. These reactions could potentially provide the energy necessary to sustain microbial life, even without access to sunlight. Europa Clipper is designed to get as close to Europa as possible, without actually landing on the surface. It will conduct dozens of close flybys, each one scanning the surface with high-resolution cameras and radar instruments, examining the chemical composition of the surface with spectrometers, and even sniffing Europa's thin atmosphere for chemical signatures that might indicate geysers ejecting material from the subsurface ocean into space. The possibility the Europa Clipper might detect geysers is particularly exciting because such geysers would provide a direct sample of Europa's surface ocean without requiring a lander to drill through the ice. If Europa's subsurface ocean is in contact with tidal heat sources in the rocky interior and is chemically active, then material from the ocean could potentially be ejected into space through cracks in the ice. These geysers would be driven by pressure from heating or by other mechanisms, potentially creating plumes that extend thousands of kilometers above Europa's surface. If such plumes exist, Europa Clipper's instruments are designed to detect them and analyze their composition, revealing information about the chemistry of the subsurface ocean. The discovery of such plumes would be transformative for astrobiology and the search for life in the solar system. It would confirm that Europa's subsurface ocean is indeed dynamic and accessible, and it would provide a way to study the composition of that ocean without requiring expensive, technology-challenging lander or probe missions. The follow-up to any detected geysers would undoubtedly involve planning future missions designed to more directly sample and analyze their composition, potentially leading to missions that deliberately try to enter and as geyser plumes as a way to study Europa's subsurface ocean. Once they arrive, they'll be adding even more layers to the already massive archive of Jupiter system data. For the first time, we'll have simultaneous science coming in from orbiters around the planet, telescopes watching from deep space, and probes diving into the ice around its moons. The Jupiter system is about to become the most explored, most studied, possibly most surprising part of our entire solar system. And all of it, every image, every flyby, bringing us closer to understanding not just a planet, but a whole miniature system or system orbiting giant world. The arrival of JUICE, Europa Clipper at Jupiter, will mark a new era in our exploration of the Jupiter system. For the first time, we will have the capability to simultaneously observe the planet itself with high-resolution imaging, study its magnetosphere and radiation belts, observe its moons from orbit, and conduct detailed investigations of its most interesting moons. The data returned from this armada of spacecraft will dwarf the amount of data we currently have about Jupiter and its system. Scientists will be occupied for years, perhaps decades, analyzing the data returned by these new missions, making new discoveries, and continuously refining our understanding of how planetary systems work. All these stunning images might seem like eye candy. They're doing a lot more than just looking pretty. Every swirl, every color gradient, every oddly shaped storm, a data point, a puzzle piece in something much bigger. And when scientists analyze these images, they're learning things that textbooks never covered, Let's start with Jupiter's atmosphere. Before Juno, we thought the weather was mostly skin-deep, just surface-level chaos. But now, with Juno's microwave radiometer and those high-resolution photos, we know the storms go deep. Some of them sink hundreds of kilometers into the atmosphere, pulling heat and chemicals down with them. That changes everything about how we model gas giants. Jupiter's storms aren't just swirling gas. They're vertical towers, more like weather systems on Earth than anyone expected. Then there's the Great Red Spot. From the outside, it just looks like a big red oval. But with detailed tracking from Hubble, Juno, and Webb, scientists have discovered it's shrinking, but also getting taller. That means the energy driving it might be changing, possibly transferring deeper into the planet or across the atmosphere in new ways. The colors in the images, they're not just for show. Different hues reflect different chemicals. Some areas are rich, and others is in sulfur or phosphine. And when you track how those colors shift over time, you can actually watch chemicals moving through Jupiter's jet streams, following smoke across a storm. Then there's the magnetosphere. Jupiter has the strongest magnetic field of any planet in the solar system, 20,000 times stronger than Earth's. And Juno's data combined with the shape of auroras captured by Hubble and Webb is revealing strange variations in that magnetic field. It's not symmetrical, it's lopsided, and the field lines dive deep into the planet, suggesting there's something unusual going on inside. Maybe even an unexpected type of core or liquid metallic hydrogen behaving in a way we don't fully understand. The scientific implications of these discoveries extend far beyond simple cataloging of atmospheric features. Understanding Jupiter's atmosphere requires understanding physics scales, and in conditions unlike anything found on Earth, Jupiter's atmosphere operates at pressures millions of times higher than Earth's atmosphere at the surface. Temperature from hundreds of degrees Kelvin in the deep interior to just 110 Kelvin in the upper atmosphere. The chemical composition is completely different from Earth's, dominated by hydrogen and helium with only trace amounts of heavier elements. Yet despite these differences, many of the fundamental physical principles governing atmospheric dynamics should be similar. Understanding how fluids rotate, how pressure gradients drive winds, how energy is transported through convection and radiation. These principles operate on Jupiter as they do on Earth. By studying Jupiter, we're studying how these principles play out in an extreme environment, learning what aspects of atmospheric dynamics and what aspects are specific to particular conditions. The discovery that Jupiter's storms extend deeply into the atmosphere was unexpected, because models suggested that storms would be confined to shallow layers near the cloud tops, where energy from the sun is absorbed, and where visible light helps drive convection. Instead, we're finding that storms can extend down hundreds of kilometers, tapping into energy sources deep within Jupiter's interior. This suggests that vertical mixing in Jupiter's atmosphere is far more vigorous than previously appreciated, and that energy from the deep interior plays a more significant role in driving weather systems than we previously thought. This has profound implications for understanding Jupiter's overall energy budget, and for understanding how heat flows from Jupiter's interior to its surface and eventually into space. The colors visible in Jupiter's image encode information about the chemical composition of the clouds. Different compounds absorb and reflect light differently at different wavelengths. Ammonia ice looks white or pale-colored, while sulfur compounds appear yellow, orange, or red. By analyzing the colors in Juno's images, scientists can infer the chemical composition of different regions of Jupiter's atmosphere and track how these compositions change over time. Some of the red coloration that gives the Great Red Spot its distinctive appearance is believed to be two organic compounds called tholins, which form when ultraviolet light from the sun their organic molecules in Jupiter's upper atmosphere. These tholins then condense and precipitate into the clouds below, carrying their reddish color with them. The exact mechanisms for their formation and transport are still being studied, but the ability to track changes in these colored regions over time gives us insights into the chemistry and dynamics of Jupiter's atmosphere. When a storm system moves to a different latitude, the color of the clouds it encounters may change. This change in color reflects a change in chemical composition, which in turn reflects different temperature and pressure conditions at that latitude. By tracking these color changes, scientists can infer information about how chemicals are being transported through Jupiter's atmosphere, how temperature varies with latitude and altitude, and how different regions of the atmosphere interact with each other. Io's volcanic eruptions, those aren't just geological events, they're reshaping Jupiter's environment. When Io erupts, it sprays sulfur and sodium into space, feeding the planet's radiation belts and creating glowing clouds of plasma that wrap around the entire planet. In some Juno images, you can actually see traces of these glowing tori. Faint. And those mysterious high-altitude jet streams discovered by Webb, they don't just move fast. They might be connected to deep atmospheric layers that we never thought existed. It's like finding an entirely new weather system sitting above all the others. Together, these discoveries are building a more complete and far more complicated picture of Jupiter. It's not just a ball of gas. It's layered, dynamic, and full of internal feedback systems. Storms rise and fall. Gases cycle through bands and plumes. Magnetic fields twist and pulse. It's living machine run in physics we're only just starting to decode. And that's what makes these images so powerful. They're not just snapshots. They're evidence of motion, of depth, of processes happening in real time on a world that's still hiding countless secrets. The glowing Tauri's Jupiter, created by material from Io's eruptions, represent a remarkable connection between a small moon and its parent planet. These toroidal structures of ionized encircle Jupiter, carrying an electrical current that flows between them and Jupiter's atmosphere, creating the auroral displays visible at Jupiter's poles. The tori are in infrared wavelengths, glowing with the characteristic radiation of ionized sulfur and other compounds. By tracking changes in the brightness and extent of these tori in images from Juno and other instruments, scientists can infer how Io's volcanic activity is changing over time. If a particular volcano on Io suddenly is more active, the tori should brighten and expand as more material enters Jupiter's magnetosphere. If volcanic activity decreases, the tori should fade and contract. This connection between Io's geology and Jupiter's magnetosphere is just one example of the complex, interconnected nature of the Jupiter system. Jupiter doesn't exist in isolation. It's connected to its moons through gravity, through magnetism, through the exchange of material and energy. Understanding Jupiter requires understanding its entire system as a unified whole. The high-altitude jet streams discovered by Webb were perhaps the most tantalizing, unexplained feature of Jupiter's recent discoveries. These jets move at speeds exceeding 500 kilometers per hour, far faster than the typical wind speeds in the visible clouds. They exist at altitudes above the ammonia cloud layer, in regions where visible light observations are impossible, and where only infrared can see. The existence of these jets suggests that Jupiter's atmosphere has a more complex vertical structure than previously imagined. They may be connected to deep atmospheric layers through mechanisms we don't yet fully understand. One possibility is that these jets are wave phenomena, similar to jet streams on Earth. On Earth, jet streams form when there are temperature gradients in the atmosphere. Warm air and cold air meeting at a particular altitude can create a shear flow, where the wind changes speed and direction rapidly across a small vertical distance. This shear is unstable and leads to the formation of waves and jets. Perhaps something similar is happening on Jupiter, where the interaction between different atmospheric layers creates high-speed jets. Another possibility is that these jets are maintained by energy from below, with heat rising from deeper in Jupiter's atmosphere drive convection that generates high-speed winds in the upper atmosphere. Yet another possibility is that these jets are electromagnetic in nature, with Jupiter's magnetic field actively driving wind patterns through electromagnetic coupling between the magnetosphere and the upper atmosphere. Only with more detailed observations and more sophisticated theoretical modeling will we understand which of these mechanisms is actually responsible for the high-altitude jets. The Jupiter system that we're beginning to reveal through modern observations is far more complex and dynamic than we ever imagined. It's not just a planet with some moons. It's an interconnected system where the planet's atmosphere, magnetosphere, and the moons all influence each other in profound ways. Io's volcanism feeds Jupiter's magnetosphere. The magnetosphere influences Io through electromagnetic coupling. Jupiter's atmospheric weather patterns are driven by internal heat sources as well as the external input from the Sun. The moons of Jupiter experience heating from Jupiter's gravity, which shapes their geology and potentially their habitability. And the interactions between all these components create feedback loops and emergent behaviors that can't be understood by looking at each component in isolation. The stunning images we're seeing now are just the beginning of what we'll learn about Jupiter. As more missions arrive, as our telescopes become more powerful, as our theoretical models become more sophisticated, we'll continue to peel back layers of mystery and reveal new depths of complexity. Jupiter is teaching us that nature is far more creative than we give it credit for, that the simple models we create in our textbooks often fail to capture the true complexity of real systems, and that the universe has a way of surprising us if we look closely enough.